Okay. So welcome another Go seminar. Today's speaker is Michal Opler, and he will tell you something about optimization with pattern-avoiding input.
So this is joint work with Benjamin Berenson and Laszlo Kozma, both from University of Berlin. In particular, I have to thank Benjamin for most of the animations that you will see in the slides. So took them from his slides. And so today, I'm going to talk about two optimization problems. I stated three in the abstract, and we have three in the paper, but for the sake of time, we'll just consider two of them. Just the dynamic offline binary search tree and Euclidean traveling salesman problem. So the first one is essentially somehow on a given input sequence, rebalancing binary search tree such that all the points can be accessed in sort of small time complexity. And the Euclidean TSP is just given a set of points in a unit square, find the shortest traveling salesman. Visiting all the vertices. So the first one is the dynamic offline inverse key. So first let me. So these problems are very well understood what happens in general, and we will go over the general cases. But our focus is on sort of inputs that have some structure. Inputs that are not coming from all the possible inputs, but rather just somehow they have some structure contained in them beforehand. And in particular, we consider the structure imposed by avoiding certain pattern. So pattern is a permutation, where permutation of length n is just a sequence of n values from the set 1 up to n. So like here, 1, 3, 4, 2. And any sequence, not of integers, but of real numbers, we say that it contains the permutation pattern pi if it has a subsequence in the same relative order. That's order isomorphic. So in here, I hope you can see the red letters a little bit. So the 1, 7, 9, and 6 is order isomorphic to 1, 3, 4, 2. Meaning if you kind of forget about the specific values, but rather about the comparisons between them, it has the same shape. And if such sequence does not contain the permutation pi, then we say that it avoids the pattern. And moreover, this extends to point sets. So for any sequence, we can represent it in a plane by plotting it out, sort of using I as the x value and the ith value of the sequence as the y coordinate. So that would be 8, 5, 1, 7, 4, 3, 2, 9, 6. And again, in this visualization, the containment of a pattern 1, 3, 4, 2 can be seen by these 4 dots having the same relative shape, kind of stretched out, but the same. There are the same relationships between these 4 points as there are in here. And we can also, so now we're talking about sequences represented as point sets, but we can also talk about pattern avoiding point sets themselves. You just get the point set, and then there are no 4 dots that would have this particular shape, and then the point set would be 1, 3, 4, 2 avoided. So really, we kind of consider also point set patterns and permutation patterns. All right. So now to the first problem. So I hope you all know binary search trees. You should know binary search trees. And this concerns a specific a model where you're given input sequence, a permutation of n keys, and your task is to design sort of a balancing tree, like specifically balancing a tree in order to keep the cost of the excesses as low as possible. So formally, you in the model, you start with some initial binary search tree. So here will be an example on input 1, 3, 5, 2, 4. So let's say I start with this particular binary search tree. And then in each step, I pick a subtree that contains the path from root to xi. That's sort of the excess I have to make because I have to find xi. But also I can pick any, in this case, I pick only the excess path. And then I am allowed to replace this subtree, the prime one, with any other binary search tree on the same number of nodes. So in this case, I choose to replace it with this tree, and then all the remainder of the original tree I just hang. So I just forward the pointer to the correct locations, and I continue the same way. So now I have to access 3. I choose to, it's in the root. I don't select any larger tree, so I just replace it with the same single point binary search tree. Then I have to access 5. Again, I choose this, but I also choose to replace it by this, which essentially simulates a rotation, right? And finally, no, almost finally, I have 2. So I choose to take this whole subtree and replace it by this subtree, again, moving the rest of the tree, hanging it where it belongs. And finally, 4 is in the roots, so I just access it. Now, the point of this is that you may think about binary search trees by working by rotations, but this is like more general because cost of each of this step is exactly the size of the tree you're replacing. And you should know from AG1 that you can take any 2 binary search trees on the same number of vertices and rotate one into the another with linear number of rotations. So you could have done this all via rotations, but it's just cleaner to say like you take any subtree at that point which contains the root and the element you're searching for, and just replace it with any other subtree or any other tree on the same number of vertices. So I hope this is clear. Right, and then there are several questions that are connected to this. So the first obvious one is, well, I give you a specific sequence, the whole sequence, well, give me the best possible way to serve this, like the best possible way of choosing these subtrees such that overall I'm spending the least amount of time. But perhaps the more, which is in itself and then becomes a problem. But the more interesting one is the question proposed by Sleator and Tarjan in 8.5, which is, well, is there an online algorithm that gets this input revealed one by one, but in the end, achieves cost that is within a constant factor of the offline optimum, right? And in particular, the dynamic optimality conjecture was that if display trees, in particular, as one type of this balancing strategy, actually achieve this constant competitive ratio, that they are only constantly worse than what would you get if you knew the whole sequence and designed these rebalances as you wish. I mean, we're still, I would say, almost nowhere near to proving this dynamic optimality conjecture, but it's one of those big questions. And kind of lately, it's been understood more broadly, not only that if display trees are the binary search trees with this property, but if there is any Bayes balancing strategy with this property. So in particular, there is one other candidate that is called GD, very interesting name. But anyway, that's a big question. And then what also people were considering, starting in fact with this original paper, is what happens if you take some sort of specific input. You might think of inputting things that are, well, sort of stupidest example is just taking an increasing sequence. Okay, it's not interesting, but as long as you start doing something slightly more involved, like taking an order which is given by pre-order of some binary search tree, then already analyzing what splay trees do on these kind of sequences turns out to be extremely hard, and in many cases is still very not understood. And all of these kind of very specific things like pre-order sequences, post-order sequences, what they call double-ended queue sequences, they can all be generalized by the fact that they avoid some permutation patterns. So kind of if we show something for pattern avoiding inputs, then it applies to all these specific cases that people were considering. That's kind of the advantage of taking this general pattern. But first, so we'll focus on this one. But first, what is even the worst case, right? Because I mean, we know the famous lower bound for sorting, but this does not quite apply here, because if you're talking about the offline version, you know the whole sequence. You can design your binary search tree to whatever way you want. So it doesn't just follow from the sorting lower bound, but it follows from encoding lower bound. So really, the worst case cost over all sequences of length n is still n log n. So and the way you would see it is, well, if you, assuming that the cost is smaller, you would be able to encode all permutations into too few bits, because any excess sequence of cost C gives an input encoding of the input in linearly many bits in C, where you just encode the shape of the initial tree, which you need only something like linear many bits, and then in each step you just encode the shapes of the two trees that you are modifying, together with the location of the element you're searching for. And that takes, again, linearly many bits in size of these trees, because you don't have to encode the actual values that are searched within the tree. So just encoding the shapes because the values are given by the sequence. They're sort of universally there. They're, in case of permutations, they are the values 1 up to n. So you don't have to encode them, you just encode the shapes. And so if you could achieve cost that is better than n log n, then it means that you could encode all permutations of length n in 2 to the middle of n log n bits. And that's not possible because the number of permutations is n factorial with more than this. So in the worst case, you can't do anything better than n log n, meaning kind of log n amortized per one of these excesses. And you have splay trees, you have all these online strategies that work well to provide you an upper bound for this. That's the worst case is perhaps not that interesting. But this lower bound does no longer applies to pattern avoiding inputs. So, and the reason is that whatever pattern you choose, the number of by avoiding permutations of length n is only exponential. It no longer grows super exponentially like all permutations, but it is 2 to the O of n. And this was actually, so first it was reduced by Martin Kozma to a, this was known as the Saranurak conjecture. And it was first reduced by Martin Kozma to a different conjecture, the Pettie conjecture, which was then resolved by Marcus Stadler in 2001. And therefore, we can hope for such an lower bound, and in fact, we could hope for achieving linear cost, and that's what we're aiming for. But very little was known before. So what was known before is that if you take union of k increasing sequences, then you achieve linear cost. Well, it's n times the number of sequences you have there squared. It was known that for patterns of length 3, you achieve linear. In fact, the result is slightly more general, but I would have to do a lot of other definitions to say that. And for general pattern pi, the best previously known bound was by these authors, and it's 2 to the O of alpha n times n, where alpha n is the inverse-Ackermann function. So this whole thing grows very, very, very slowly, even though it looks like exponential, but don't be fooled, this is extremely small. And also surprisingly, they showed that they used some sort of methods from extremal combinatoric extremal theory of matrices, and they showed that their methods are actually tight, like that they can't do better bound using their methods. Like extremal combinatorics is a place where all these weird functions, very slowly growing functions, appear quite often. And anyway, and moreover, all these results, I have to mention that all these results were obtained in the online case. So they were actually, they applied to one of these online balancing strategies, not only in the offline case. There was in fact no specific result, I think, known only for the offline case. And our goal and our result is that for the offline case, we can in fact serve them in linear time. So for any fixed pattern, we can design and access the sort of sequence in this offline dynamic BSP that achieves linear cost, where there is some constant hidden depending on what the pattern is. But what's first most surprising is that we completely leave the binary search trees and go to a purely geometrical problem, which is like still to this day is one of my favorite parts of this is that it somehow transfers to a completely geometric problem. And the idea is, well, you plot the execution of the binary search tree as a point set, where you have the input, right? So you have this axis are the keys, and this is how they are arranged in time. And then you add points like to all the nodes that were touched at a given time. So at this second time, this first node was also touched by the algorithm, meaning it was part of the tree that was replacing. And clearly, like what I'm interested in when I'm talking about cost is just size of this set, right? Sort of the input plus all these extra excesses that I have there. And it turns out that these point sets have a very nice characterization, which is that they are what we call arbitrarily satisfied, which means that every pair of points spans either non-empty or degenerate rectangle. So if you look at any points in such point set, they will either have some point either inside or on its boundary, or they will be degenerate, meaning that they will share one of the coordinates. But never you'll encounter 2 points with an empty rectangle, completely empty rectangle. And this is actually characterization. So an excess sequence, like the input to the offline dynamic VST, can be served at cost C if and only if we take the point set of the sequence, then it has arbitrarily satisfied superset of size exactly C. So it's like exact characterization, like if you take the VST problem, transform it to the point set, then asking about the optimal offline VST sequence is the same as asking about this arbitrarily satisfied superset. So let's rephrase our goal. Now we don't care anymore about the original problem, but we now try to show that if we take any pi-avoiding point set, then we can find an arbitrarily satisfied superset of size linear in the original set. Okay. And now we take one extra side step. So we'll apply twin width to this. So some of you perhaps have heard of twin width. So before properly defining what it means for twin width of permutations of point sets, we just take a slide to say that it's a very useful thing. It's some sort of complexity measure, some sort of structural parameter for permutation graphs and other relational structures. It was originally introduced by Dimot and Marx in 2014, but that was only for permutations, and it was not even under the name twin width. We just called it width. And then in 2021, there was this seminal paper by Bonner et al. That they kind of transferred this idea to graphs and more generally relational structures. And it's defined using some sort of decomposition, merge sequences, which we will see in the next slide. But let me just note, there's many different use cases of bounded twin width, ranging from FTP algorithms, some sort of approximations, and all the way to some combinatorial results like polynomial high-boundedness, etc. But for us, one thing is important the most, and that's that in fact somehow permutations being pattern avoiding and having bounded twin width is equivalent. So that was actually proved by Dimot and Marx that every pi-avoiding permutation has twin width constant, where the constant is not just some constant, is clearly high null limit of pi. I realize that you don't know what that exactly means, but it's a limit that comes out of the original clearly high null conjecture, and it's sort of extremal result from extremal common theory of binary matrices. But the important thing is that every pi-avoiding permutation has a constant twin width. And so if you remember the previous slide, we were trying to, for every pi-avoiding set, find an arbitrarily satisfied superset of linear size. Well, we rephrase this once again. Now we just look at point sets of bounded twin width, and we want to show that point sets of bounded twin width have arbitrarily satisfied superset of linear size. And this will be, in fact, what we will do. It's the final formulation of this fact. Now the promised definition. So bear with me, it's not that complicated. It's actually much easier than with graphs. The merge sequence is a sequence of rectangle families, where rectangle family is just a set of axis parallel rectangles, and a point is just a degenerate axis parallel rectangle with side length 0. So when you start with the point set, you have a rectangle family. That's the point set. And at any point in the sequence, you take two of these rectangles and replace them by their bounding box. And then you continue all the way up until you get a single rectangle. So now I choose these 2 points, replace them by their bounding rectangle. These 2 points, the same thing. Now these 2 rectangles, I replace them by bounding box, and etc. These two, and I continue all the way up until the whole thing is merged into a single rectangle. Now the question is, how do we measure complexity of this, right? So I can merge them in many different ways, and somehow I want to say which is nice with some sort of nice properties. It turns out the way to do it is to sort of define it through the means of rectangles that see each other. And we say that they see each other if their projections on one of the axes overlap. So either they look like this, where in this case their projection on the y-axis overlaps, or their projections on both axes overlap, which means that they in fact overlap as objects. But these rectangles do not see each other, because they're on both axes, their projections are completely disjoint. And the idea is that if I have these two rectangles and I take any point in here and any point in here, then I'm guaranteed that they will have the pattern 2, 1. Whereas when they see each other, then somehow it depends on where I pick the points inside the rectangles. So these are kind of like nicely behaved. And then we say that merge sequence, this sort of sequence of rectangle families, is dy if no rectangle sees at any point more than d minus 1 other rectangles. So we have rectangle family like this, and this one 3. So this one sees 3 rectangles, this one sees only 2 rectangles, this one sees 5 rectangles. All of the other ones. Meaning that if this rectangle family was in our merge sequence, it must have been at least 6 wide, because there is some rectangle that sees 5 other rectangles. And the twinlet is just the smallest d such that there is a d-wide merge sequence. And these edges between rectangles that see each other are drawn in red. It's because in the sort of graph definition of twinlet, they talk about this red graph, which exactly captures these objects that somehow interact. And then you're essentially looking at the degree in this red graph, which is exactly how many rectangles are seen by a given rectangle here. Okay. Right, so now what we were aiming to do is to show that the points that are bounded twinlet has a linearly sized, arbitrarily satisfied superset. And in fact, the construction is quite easy, and I won't prove the correctness, but I'll show you how to do it. So assume that we have some d-wide merge sequence, and we just repeat these things. We form a grid from all the rectangle sides. So at the beginning, it's just all the lines of all the grid. And then we execute the next merge in the sequence. So we merge these two rectangles. And we simply add all grid points that are within this new rectangle or on its boundary. So in this case, all of them, because the grid is still complete. And we continue. Like, now nothing happens, but later, when we go back to step 1, some of the rectangle sides have disappeared, so the grid might have gotten sparse. Right now this does not happen, so we execute the next merge. Again, add all the grid points within this rectangle. Again, nothing happens with the grid. We take the next merge, and again, add all the grid points. But now, suddenly, no, the next step. Still nothing happens. You again do the next merge. Again, all the grid points get added. But now, suddenly, all these lines have disappeared. They're no longer sides of the rectangle. So the grid becomes sparser. And we again continue executing the next merge, and now adding only the grid points with respect to this new grid. And again, and again. Now again, the grid gets sparser at this point. We execute the next merge, add all the merge points. And we continue this all the way up till the end. And we end up with this thing. I mean, it's a sort of interesting process, because on one hand, the rectangles are getting bigger and bigger as you go along the merge sequence, but the grid's getting sparser and sparser, and somehow in total you end up only with linearly many extra points, and moreover you guarantee that any pair of points is arbitrarily satisfied. Okay. Check it here if you wish. Right. So and like I said, I will not prove the correctness, so you have to trust me the arbitrarily satisfied part. Essentially, you set up a nice invariance and you prove that they hold throughout the whole process. That's the way to do it. But what is easier to see is that the number of points is linear. And in fact, we claim that in every step of this process, we added at most d squared points. And this is exactly because that was a d-wide merge sequence. So at any point, this newly created rectangle see at most d other rectangles. And those are the only rectangle sides whose line can actually lie within this rectangle R, right? So if I have a rectangle that is not seen by R, then the grid lines given by this rectangle are completely independent of R and will never add a grid intersection point inside R. So they are only added by the rectangles that are seen by R, and since there is at most d of them, well, then the rectangle intersects at most 4d grid lines, and therefore there can be at most something like 16 d squared points.
So d squared, so how come this is linear?
Because it's for bounded twin width, right? So we assume that d is a constant. In particular, for pattern pi is the Fidelity high null limit of pi, and we get that for every input sequence of twin with D, the cost of this offline dynamic DST is at most D squared n. And therefore, for every pi avoiding input sequence is this Faraday high null limit squared. Okay, so that was the whole first problem. And now let's jump to the second one, to the Euclidean traveling salesman. So again, the definition is easy. You're given a set of endpoints inside the unit square, and you're asking about the shortest tour visiting all vertices of phi. Let us denote this by PSP of phi. And now, well, in fact, we will consider minimum spanning tree because we only care about asymptotics. So our problem will be Euclidean minimum spanning tree, where again we get endpoints inside the unit square, but we are interested in the length of the minimum spanning tree, not of the shortest tour. This will be denoted by MST. And why I say that these two things we don't care about that or that, it's because it's quite well known, it's easy observation that the traveling salesman, length of the traveling salesman tour is at least the length of the minimum spanning tree, and at most 2 times the length of the minimum spanning tree. Right? So on one hand, if you give me a traveling salesman tour, I can just delete one edge and get a minimum spanning, get a spanning tree, which upper bounds the minimum spanning tree. And on the other hand, if you give me a minimum spanning tree, I can first transfer it to this sort of closed walk that walks around the spanning tree, which is of length twice the original solution. And then I just start walking around, but whenever I would visit a vertex that is already visited, I just skip and take a shortcut. And this way I walk around the whole all points, and I get a solution for the traveling salesman that's at most 2 times the minimum spanning tree. And now we will play the same game as before, meaning, well, we asked about the worst case. What is the longest tour you can get with the worst point sets that you can get? And in fact, this has been resolved for quite a long time, that the worst case cost of minimum spanning tree, if I give you n points inside the unit square, is actually square root of n. And let me just show you, because that's, I think it's nice how it's done. So the upper bound, how to construct such minimum spanning tree, is you take your set of endpoints inside the unit square, and you draw this grid that's of size square root of n times square root of n, right, with each sort of this square side of 1 over square root of n. And then you connect everything inside each of these squares, which gives you cost of square root of n, because whatever edge is there, it cannot be longer than square root of 2 over square root of n, because that's the length of the diagonal of each of these squares. And then you just add bogus points to the empty squares and connect them, kind of connecting the shortest neighbor, taking a minimum spanning tree of these representatives. And again, because you're at the worst case, you're connecting something that's roughly 2 squares away, then you're taking linearly many edges of this length, and again, that sums up to square root of n. So that's the upper bound, that this order is always suffices, but also the lower bound is super simple. Take a grid, and now there is no edge between 2 points that it's of length shorter than 1 over square root of n. So I have to take at least n minus 1 of those because it's a spanning tree, and therefore I get this. But observe that, in particular, this kind of lower bound, it contains all patterns of length at most square root of n. Right? So it's like a very not pattern avoiding. It in fact contains all of them up to some length. So this gives us hope that something better, something nice happens when we restrict the inputs to be pattern avoiding. And in fact, it does. So it collapses to logarithm of n. So if you have a point set inside this unit square, which is pi avoiding for some pattern pi, then the minimum spanning tree of this particular point set is always at most of length at most logarithm n, with some global constant depending on pi. So 2 easy examples which can be done like immediately is the annoying one is like the really easy one is if you have a decreasing sequence, right? And perhaps you would guess how to construct a short minimum spanning tree of this. Right? You just connect them into a path, which is of a constant length. And then if you have something that avoids 1 to up to k, then it means that the input can be decomposed into k minus 1 decreasing sequences. So you do the same thing with each of these k minus 1 sequences and then join them by a single path, joining their last points, which gives you something that's linear in k. So we already see that for monotone patterns, it's in fact better than log n. It's just always a constant. But that was easy to show. And now for the general case, we actually have to go back to this Guillemot and Mark's result that states that every pi-avoiding set of endpoints admits a constantly wide merge sequence. And so we improved this because we somehow want to use this merge sequence to construct the minimum spanning tree, somehow in a greedy manner. But we have no control over how large these rectangles are, how weirdly interacting they are. And then we managed to show that, in fact, for every pi-avoiding set of endpoints, it admits something that we call distance-balanced merge sequence of the same, again, wideness, where, in particular, the width and height of the ith created rectangle is at most kind of linear in 1 over n minus I. So the rectangles, it behaves like you would expect that the first rectangles you create are really small because you're connecting the points that are nearby. And as you go along, you're forced to make larger rectangles, but they're somehow inversely proportionate to how far along you are in your merge sequence. And I mean, the distance balanced merge sequences we derive are in fact more complicated. They have several other balance properties, but they're not needed for this problem, so I'm not stating them here. For this one, it suffices to consider these heights and widths. And now, having this improvement of the decomposition theorem, it's easy. You just take a distance balanced merge partition, you replay the merge partition, the merge sequence, and whenever you merge two rectangles, you just connect arbitrary 2 points. So just right, you connect 2 points, connect 2 points, connect 2 points. Here you merge this with this rectangle, so you connect arbitrary 2 points within the new rectangle. Again, you merge these two rectangles, you just connected 2 points in there. Same here, same here, same here, and we arrive with this. And because the rectangles grow in this nice fashion, right, that they're small, then if we sum the overall cost, we're essentially summing the fractions 1 up to 1 over 1, 1 over 2, 1 over 3, all the way up to 1 over n, which is the logarithm, which is the nth harmonic number, essentially. And so we have the cost of logarithm n. And if you care about the constant, the dependence of this cost on pi, then it's this, again, clearly high null limit. This time it's not squared, it's just here as a linear factor. Okay, so that's all to this. So let me conclude. So we've seen that the pattern avoidance reduces worst case optimums for different problems. So we've seen the two of them, the offline dynamic BST from n log n to n, and the Euclidean MST from square root to logarithmic. What was not here, but it's in the paper, that if we consider k-server problem on the line, then it reduces from n over k to something like n to the 1 over log k. So essentially something like n to epsilon, where you can choose epsilon as small as you want. And the tools in this were the bounded twin width and Marcus-Dash theorem, which I haven't had to introduce here, but it's the driving force behind that structural decomposition theorem. It's a combinatorial result that's actually allowing, and it's behind all the twin width machinery. It's kind of the key result in this area about binary matrices. And in particular, the BST result is interesting because it serves, you can look at it positively and negatively. The positive way is if at any point somebody proves that splay trees or other BST balancing strategy is dynamically optimal, then you immediately know, for instance, that you can sort pattern avoiding sequences in linear time because we have this offline linear cost. So therefore, this online strategy must also take at most linear time. But on the other hand, it's also a barrier to proving, in some sense, for data structure, for some sort of BST balancing strategy to be dynamically optimal, because this has to hold for it. So in particular, if splay trees are in fact dynamically optimal, then they have to sort every pattern avoiding sequence in linear time, right? So it's yet another property that they have to have in order to be dynamically optimal. And the interesting question here is, well, we only were able to do it in the offline regime, but it's interesting whether we can show this linear upper bound for some of the online algorithms, for either splay trees, which seems unlikely because most of these pattern avoiding things are completely, like, are really not covered for splay trees, but it might be possible for these greedy BSDs, which actually it's an algorithm that comes from the geometric reformulation, so it's in some sense very close to the patterns. And finally, well, are there any other optimization problems that behave similarly, that also the worst test reduces quite significantly when going from unrestricted inputs to inputs that avoid some pattern? And as I said, the pattern avoidance might not be the good thing to view it is as a sort of a common root over many input sequences with nice properties, and you proving for all of the families at once by proving for any pattern avoiding inputs. Okay, that's it. Thank you.
Okay, are there any questions?
So for the MST, you showed the logarithmic upper bound, and so that for the monotone sequences, you can do it in constant, constant. Is there a characterization of the sequences that have like this?
Yes.
I'm basically asking for the lower bound.
Yes, and it's exactly like this. So for monotones are the only ones that have constant, and all the other ones have logarithmic lower bound. And in fact, what we also know, and I haven't had time to go into, is that if you take 2-3-1 avoiding patterns, 2-3-1 avoiding inputs, then they have logarithmic cost. But if you take any subclass of these permutations, if you add any arbitrarily long other avoided patterns, then it already goes to constant. So we have this sort of transition, phase transition thing. Yeah.
If not, I guess we can just keep again.